Right, this is the second video on section 6.2, that is properties of power series. We're going to be looking at multiplication of power series and also integration and differentiation with power series in this video. So first we're going to start off with multiplying power series. Suppose that the power series sum n equals 0 to infinity c sub n x sub n and the sum n equals 0 to infinity d sub n x sub n converge to functions f and g respectively on a common interval I. Put e sub n to be equal to c naught d sub n plus c1 d sub n minus 1 plus c2 d sub n minus 2 plus dot 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 c sub n minus 1 d sub 1 plus c sub n d naught. And what you're looking at there is the powers. So this would, the c naught would go with x to the 0, d sub n with the x sub n, c1 with x, d sub n minus 1 would be x to the n minus 1, c sub 2, x squared, d sub n minus 2, x to the n minus 2. All the way out to c sub n minus 1 would be x to the n minus 1 would be the polynomial attached to it. D sub 1 would have an x to the first, and then finally c sub n would be the coefficient on xn, and d naught would be the coefficient on x to the 0 power. Now if we add up all those powers there in each respective pair, this would be x to the n, etc. And we write that as the sum k equals 0 to n c sub k d sub n minus k. And then if we wanted to put it into the series, all we need to do is put the x to the n on there. And so that's how we do the multiplication of two power series. In practice, what we're going to want to do is write out a number of terms for both series and then multiply term by term and kind of see if we start noticing some patterns. So, in example number 4, we're going to multiply f of x, which is the sum n equals 0 to infinity of 2x to the n, and g of x, which is equal to the sum n equals 0 to infinity of n x to the n. And so we're going to go ahead and multiply those term by term. So f of x times g of x. So each term in f of x has a 2, so we're going to factor a 2 out. And so that'd be 2, and then 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th, etc. Now g of x, the first term is going to be 0x to the 0, so it's going to be 0 plus an x plus a 2x squared plus a 3x cubed plus a 4x to the 4th plus 5x to the 5th, and etc. And so what we're going to try to do is we're going to see if we can notice some sort of pattern when we start doing the multiplication. Okay, so I'm just going to have the 2 out in the front, and the first thing I'm going to do is I'm going to distribute the 1 to everything into the second series. So 1 times x, 1 times 2x squared, 1 times 3x cubed, 1 times 4x to the 4th, plus 1 times 5x to the 5th, and that just keeps going on. Okay. And now we're going to take the x and we're going to multiply the x by everything in the second series. So x times x is x squared, x times 2x squared, 2x cubed, and etc. Just multiply each one of those terms by an x, so it increases their power by 1. And then we're going to multiply everything by the x squared in the second series. So then it gives us x cubed plus 2x to the 4th plus 3x to the 5th plus 4x to the 6th plus 5x to the 7th. Okay, and then etc. And we'll do one more on this slide, and we'll multiply everybody by the x cubed. So by the x cubed is going to increase their exponents by 3. So I'm going to have an x to the 4th plus a 2x to the 5th plus a 3x to the 6th, plus a 4x to the 7th, and plus a 5x to the 8th. And we keep going. So I still need to distribute through the x to the 4th and the x to the 5th, and just to kind of get an idea what we're looking at here. So let's go ahead and move on to the next slide. Okay. So we are about right here, okay? And now we want to multiply the x to the fourth through. So if we multiply the x to the fourth through, we're going to add 4 to each one of the exponents here. So it's going to be x to the fifth plus 2x to the sixth plus 3x to the seventh plus 4x to the eighth and plus 5x to the ninth. And one more time, we're going to distribute the x to the fifth through, so it's going to add 5 to each one of the exponents. So 2 times x to the sixth plus 2x to the seventh plus 3x to the eighth plus 4x to the ninth and plus 5x to the 10th. And then what we're going to do is we're going to start grouping all the like terms. Okay. All right, so we got the 2 there, and I only see 1. That's the only constant is 1. Sorry, no, I'm looking at the wrong thing. We have a 1 up here. But do I have any constants anywhere in here? And the answer is no, there's no constants. So we're going to start off with x to the first power. It looks like there's only an x to the first power. Now we'll do the x squared. So we got a 2x squared and an x squared, which makes a 3x squared. And we'll do the cubes. 3x cubed, 2x cubed, and an x cubed for 6x cubed. We'll do the x to the fourths. Let's add those up. So we got 4x to the fourth, 3x to the fourth, 2x to the fourth, and x to the fourth. So that should be 10x to the fourth. And we'll do the fifth power. 5x to the fifth, 4x to the fifth, 3x to the fifth, 2x to the fifth, and 1x to the fifth, which gives us 15x to the fifth, and etc. And so what we want to do is to try to notice if there's a pattern for writing these coefficients. Okay, so sum n equals 0 to infinity, 2, and then we're going to see if we can come up with a pattern for these coefficients. Coefficients are 1, 3, 6, 10, 15, etc. So first thing we know is to go from 1 to 3, we add 2. From 3 to 6, we add 3. 6 to 10, we add 10. We don't add 10. We add 4. And from 10 to 15, we add 5. And so this is not an arithmetic sequence where we're adding the same thing over and over again. It's actually probably going to be a quadratic sequence. And we're going to see if we can come up with a pattern for this. So A1 is equal to 1. A2 would be equal to the previous term plus 2, and that's 3. A3 would be equal to the previous 2 terms, and then plus 3, which is 6. A4 is equal to the previous 3 terms, plus 4, which is 10. A5 is equal to the previous 4 terms, and plus 5, and that's equal to 15. Okay. If you recall from probably pre-calculus and certainly Cal 1, you have the sum 1 plus 2 plus 3 plus all the way out to the n. 1 plus 2 plus 3 all the way out to n. That ended up being n plus 1 all over 2. And so that is quadratic for a quadratic sequence here. So that is what's going to determine the coefficients here. And the next, the n. The 2's will absorb when we have the sum n equals 0 to infinity. N plus 1, x to the n, is the product of these two infinite series. Okay. All right, the next thing we're going to look at in this video is differentiation and integration involving power series. Okay, so theorem, term-by-term differentiation and integration for power series. Suppose that the power series sum n equals 0 to infinity c sub n x minus a to the n, and that's centered at a, converges on the interval a minus r, a plus r for some r greater than 0. Let f be the function defined by the power series. F of x is equal to the sum n equals 0 to infinity c sub n x minus a to the n equals c naught plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed plus dot 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 plus c sub n x minus a to the n, and etc. For the absolute value of x minus a is less than r, that's on the interval of convergence, then we're going to say that f is differentiable on the interval a minus r to a plus r, and f prime is found by differentiating the series term by term. So f prime of x is equal to, so if we took the derivative of this piece right here, the cn x minus a to the n, that's the nth term, you have the c sub n, the n would come down, x minus a, and then subtract 1 from the exponent. So that's what we got going on there. Term by term, what that would look like is the c naught, the derivative of that would be 0. The c1 x minus a would just be c1. c2 x minus a squared, the 2 would come down, and subtract 1 from the exponent. The next term, the 3 would come down, and subtract 1 from your exponent, etc. And that'll converge on the interval a minus r to a plus r. Okay. And then the third part is here, or, well, I don't know if it's the third part. The second part for integration, also the integral of f of x dx is found by integrating the series term by term. The resulting series will converge on the interval a minus r to a plus r. So the integral of f of x dx is equal to c plus the sum n equals 0 to infinity c sub n x minus a to the n plus 1 all over n plus 1. So if we took this term here, c sub n x minus a, how we would integrate that is add 1 to the exponent and then divide by the exponent. And so that's what we have exactly right here. If we do term by term integration, we certainly get a constant of integration. Here's our c naught x. We're going to go ahead and rig it so it's x minus a, and we can just play with the constant of integration to make that work. The c1 x minus a, you would add 1 to the exponent and divide by the exponent. The c2 x minus a squared, you would add 1 to the exponent and divide by the exponent, etc. And go all the way out to the nth term. When you add the 1 to the exponent, it becomes n plus 1 over n plus 1, etc. And we will have convergence on the same interval. And as an absolute value inequality, we write that as x minus a less than r. Okay? So we're going to do a couple examples here. Practice this. So we're going to evaluate the infinite series by identifying it as the value of a derivative of a geometric series. So we're going to look at the sum n equals 1 to infinity of n over 7 to the n. And then they provide us a hint. They're going to say, hint, write it as f prime of 1/7, where f of x is equal to the sum n equals 0 to infinity of x to the n power divided by 16. I think this one's going to be a little bit more complicated on the homework. I think they just give you x to the n power, so it'll be a little bit more complicated than what you see on the homework. So we're going to rewrite this, the sum n equals 0 to infinity of 1 over 16 x to the n, and that is a geometric series. The sum n equals 0 to infinity a r to the n power, just the r to the n power, is going to converge to a over 1 minus r, provided that the common ratio in absolute value is less than 1. So that is going to, that series n equals 0 to infinity of 1 over 16 x to the n is going to converge to 1 over 16, 1 minus x. Okay, so simplify that, that'd be 1 over 16 times 1 over 1 minus x. Okay? So the derivative of that is going to be 1 over 16, bring down your exponent, which is a negative 1, subtract 1 from your exponent, make that a negative 2, put it in the denominator, and then times negative 1 by the chain rule. So f prime of 1/7 is going to be 1 over 16 times 1 over 1 minus 1/7, and that 1 minus 1/7 is quantity squared. It's going to be 1 over 16, 1 over 7 over 7, which is 1, minus 1 over 7, quantity squared. It's going to be 1 over 16 times 1 over 6/7 squared. It's going to be 1 over 16 times, and then 6 over 7 squared is going to be 36 over 49, and then it's in the denominator, so we're going to flip it over, become 49 over 36, which is going to be 49 over 576. Okay, so that's what f prime of 1/7 is. Okay, now let's take a look at this series, f of x, which is equal to 1 over 16, and 1 to the 0 is 1, x to the 0 is 1, x to the first, x to the second, x to the third, all the way out to the nth power of x. And we are looking at finding the derivative here. So f prime of x is going to be 1/16, 0 plus 1 plus 2x plus 3x squared plus dot 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 n x to the n minus 1, and it keeps going. And we can write this as an infinite series, sum n equals 0 to infinity of 1 over 16 n x to the n minus 1, and then you use your nth term kind of as a cue of how that's going to look. All right, so this series, we know, has a sum of 49 over 576. It's the derivative of f, okay? So, at 1/7. So let's go ahead and evaluate this series at 1/7. So it's going to be the sum n equals 1 to infinity of 1 over 16 and 1 over 7 to the n minus 1, which is equal to the sum n equals 1 to infinity n over 7 to the nth power times 7, okay? So this right here will give you 7 in the n minus 1 over 16, okay? And we know that that is 49 over 576, okay? So what we need to do is we need to manipulate this to look like this. And it's just off by a constant, so that's a piece of cake. We can go ahead and fix that, okay? So we're going to manipulate it to look like that. So this is going to be the sum n equals 1 to infinity of n over 7 to the n, 7 over 16 times 16 over 7, so that doesn't change anything. And if you wanted to, you can slide this 16 over 7 outside of the series there. We know it's going to be a convergent series. And so the series part, this right here, is going to converge to 49 over 576, and then times the constant 16 over 7, and that simplifies down to 7 over 36 as the sum of that series. All right, now let's look at an antiderivative problem. So let's look at finding the value of the sum n equals 2 to infinity of n minus 1 over 4 to the n. And so they provide us a hint, and they say, hint, write it as f prime of 1/4, where f of x is equal to the sum n equals 0 to infinity of x to the n over 16. So from previously, this was, we just figured this one out. This infinite series is 1 over 16 over 1 minus x, provided the absolute value of x is less than 1. And we found the derivative not too long ago either, so the derivative of that was 1 over 16 times 1 over 1 minus x squared. Okay. Now, I think our hint was supposed to be f double prime, so we may need to fix that there. F double prime, we take the second derivative, it's going to be 2 over 16, 1 over 1 minus x to the third power, okay, which reduces to 1 over 8, 1 over 1 minus x cubed. And we're going to find f double prime of 1/4, which is going to be 1 over 8 times 1 minus 1 over 4 to the third power. So 1 over 8 times 1 over, so 1 minus 1/4 is 3/4. We're going to cube that. So it's going to be 1 over 8 times 64 over 27, which is going to be 8 over 27. Okay, now f of x was equal to 1 over 16, 1 plus x squared plus all the way out to x to the n, etc. So the first derivative would be 1 over 16, 0 plus 1 plus 2x plus all the way out to nx to the n minus 1. Keep going. So the second derivative would be equal to 1 over 16, 0 plus 0 plus 2 plus all the way out to n minus 1, x to the n minus 2, and it keeps going. If we write this as a series, this would be the sum n equals 2 to infinity of n minus 1, x to the n minus 2. And again, use the nth term to kind of help you with the formula there. Okay, so we have the infinite series for the second derivative. All over 16. Oops. So I think we're just going to rewrite it here. So there's your second derivative, which is f double prime of x. What we want to do is find f double prime of 1/4. So there it is. And that's going to be equal to the sum n equals 2 to infinity of 16 n minus 1, and then 16 times 4 to the n. So let's see what happened here. So we have n minus 1, 1/4 to the n, and then 1/4 to the minus 2 over 16. So that's going to be equal to n minus 1. Now, the 1/4 to the minus 2, you can flip that over and make it a square. That's where the 16 comes from. Okay, the 1/4 to the n, we can slide that to the bottom, and then we have the 16 there. So that's where that all came from. So let's get this stuff out of the way. We're almost done here. Okay, so the 16 is absorbed, so we have the sum n equals 2 to infinity of n minus 1 over 4n. And remember, the second derivative at 1/4 was 8 over 27, and that's exactly what the second derivative was this series here. So they started us off with this series, and they said, hey, what is the derivative of that? And they said, well, let's look at f of x equals the sum n equals 0 to infinity of x to the n over 16, okay, which was equal to 1 over 16 over 1 minus x, okay. Then we needed to look at the second, well, we would look at the second derivative. We need to get to the first derivative. So the first derivative was the sum n equals 1 to infinity of n x to the n minus 1 over 16, which I believe we said was 1 over 16 times 1 over 1 minus x squared. And then we look at the second derivative. So the second derivative was equal to the sum n equals 2 to infinity of n minus 1 x to the n minus 2 over 16, which was equal to 1/8 1 over 1 minus x to the third power. Okay? And we took our second derivative and we evaluated it at this, and we figured out what that was. Then we can plug in that 1/4 into this, which ended up being this thing here. And so that's how we were able to establish that the series converged to 8 over 27. Okay. Now this is a little bit of a longer section, so I do have one more video for you on the section 6.2. So we'll see you next time.